Alright guys, it's gonna be a quick update on my day 3 progress, I think. And it was a while ago, but I'm trying to update. I'm trying to like keep it up. Gonna probably like potentially update a couple more videos, but okay, let's go. So this was a physics practice test that I have done. You can like get one of these from like Princeton Review. I usually just get it from Princeton Review or Barron's. And yeah, because like you want to see the 2025 version. The versions before 25, there is no Unit 8. You gotta remember that. Unit 8 fluids is very new unit this year. So yeah. Okay, so for Unit 1, first I just thought you gotta know the center of mass formula. That's very important. And then yeah, just go through that real quick, know how to do it. And then also like know where V0 or Vx is 0. So that will help you with problem solving. So for instance, if you have a problem that asks you about when does the car stop, after an acceleration of something, or how much energy is used, that indicates how much energy it took for the ground, I guess, to make the car stop. For instance, if you have a friction on the ground, that's when some status of the velocity is equal to 0. So yeah, just remember that. And also, you don't forget associate the gravitational something like that. The g constant with ay. Whenever you're doing ay, you're accelerating up. The acceleration is just g, which is negative 9.81 meters per second. Okay, and then another one is like the fourth one is rockets usually have two parts of movement. This is very important because you just want to know it accelerates from 0 to breaking gravity, and then the second phase is just using that velocity from after breaking, from the instant of breaking gravity. It doesn't have any more vertical acceleration. It doesn't have any more negative 9.81. It will just be as it is. The velocity will stay as the same at the moment of breaking gravity. So yeah, that was very interesting. And then 5 is like the flow of water. There's this problem when you have a river, you want to get across, right? Look at this. So there's a boat getting across, and there's a river flowing down here. And if you have an initial speed, let's say like 5 meters per second, you'll be slower because the water might be like, I don't know, like 8 meters per second, something like that, going down. And then your car will be like this, and then get to the end. So for this scenario, you have like a distance you want to travel, and since you have the speed, it will definitely ask you like how much time it will take for the boat to get across the river. So basically, you want to take the horizontal component, which is like I think the horizontal component is the answer. This like the hypotenuse is actually your initial speed. You know why? Because there is a force pushing you down. The river is pushing you down. So the vertical component is the river flow, and hence your boat's speed or your boat's velocity is the hypotenuse, and then the final result is like the going through the river. All right, so okay, that's about it for unit 1. That's like all the things I thought it was interesting and good to know. And okay, unit 2, you just want to know normal force is just a force reacting against the weight. That's it. Remember that, because every time we have a surface, right, you put something on it, it's because Earth is acting on it. Like Earth has a force acting on it. That's called the gravitational force, and normal force is just supporting that weight. It's like a reaction. And what is it? One of the Newton laws. I don't even know which one it is. Newton just says every force has an equal and opposite reaction. So yeah, normal force. Remember, it's just that. And when you're doing multiple choice questions like how many forces or how many objects are involved in this system, there you go. If there is this like friction or anything like that, there must be like Earth. However, for those kind of questions, if you have two source energies, if you only have two source energies, that is like this or this, there is no normal force like this, right? So this there's only two sources. All right, there's only two sources. One source is over like here, one source is over here. So these are like for these questions. You'll get it when you see them. All right, it's hard for me to explain, but yeah, just know normal force is a force reacting against the weight. And then 7, tension describes the source of the force. Okay, So when you have something pulling at something, the 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 object that is pulling something is creating like a force or energy. So tension basically carries that force because it's like a connection between this object and let's say this object. So you're pulling it, there is the force is acted on the tension object. For instance, like the string. Okay, so remember that. All right, number 8. Remember the overall net force. It also fits in specific force scenarios. For instance, like when you have like a net force of like mg, like there's this kind of like table problems, when there are like several objects, but you have something over here. That mg applies to all of your objects because this is the only source, and the acceleration is the same because there is only one source of energy. So acceleration is the same for this block, and this block. And every time when you want to explain the force acted on each object, just multiply the acceleration with m. You get F equals ma. All right. So okay, that's that. And number 9. Oh, you wanna just know mg sign. Sometimes you wanna use it, and yeah, like when you're accelerating up, the mg sign is like the vertical, and sometimes you want to use sine for like acceleration, because uh, if you are accelerating, if you're accelerating this way, you need to multiply. You want to play with the sign, and yeah, just figure it out because this is very important for dynamics. Okay, unit 3, number 10 is okay, you really have to remember this formula. You need to know how to use it. All right, you don't have to remember it because it's on the formula sheet. So there's two different formulas: potential gravitational force formula, and then no just force, Fg. So Fg basically gives you G, like as for Earth. Actually, not G. It's like Fg equals mg. G is the gravitational constant, and if you want to calculate for different like planets, the m is just the m of the object, and then it cancels out with one of the m on the right side, as you can see over here, because yeah, one of them is the object and the other one is the planet. And then yeah, this is how you calculate the Fg. And then for potential energy, since like potential and yeah, potential gives you like sometimes, I don't know, you just want to know this. All right. Okay, so 11 is restoring force. Okay, it's good to just tell you that restoring force is always just, it's also like one of the Newton's laws, and it's basically just direction going back to the equilibrium position. For instance, if you have a string, you're going this way, restoring force will definitely try to go back to the equilibrium. And if it is here, it's gonna go back here. All right. So okay, 12 is rotational inertia. Okay, just take a look at it real quick, like rotational inertia of disk. For instance, let me search it up real quick. So you have different rotational inertias for different things, and this thing, I think, is smaller than this. Ring is smaller than mass, and oh yeah, this one you gotta remember. Ring is smaller than let's say ring is smaller than, oh, ring might be actually bigger, chat. Wait, hold on. Yeah, ring is bigger because like the mass is distributed in a less volume. Like the size is smaller, but the mass is the same. So its rotational inertia is larger because there's more mass distributed on the outer layer. Yeah, whenever your mass is distributed on the outer layer, that requires more torque. That's why inertia is larger. So yeah, that's something good to remember. I'm just gonna put that down because whenever the mass is distributed to the outer layer, the outer it is, the more torque it is required to spin its larger rotational inertia. This makes sense because torque equals Rf, and F is the vertical component of the force, and R is the distance from the center to the force source. Okay, number 14. In circular motion, centripetal force means, okay, so if you have something that's accelerating down, like a ramp, it's if it is like circular on the bottom, all right, if it is a roller coaster, for instance, this place has a centripetal force because there's something that is like accelerating towards the center, all right. It's just a phenomenon. Centripetal force is basically like a explanation. It's not an effect. It's just an explanation of an effect, all right. It's not like a character. It's not like a special thing that happens. It's just an explanation. So it happens when you're accelerating up. Yeah, you get it. Like a roller coaster, you're accelerating up. If you imagine you being on a roller coaster. I haven't been to one in years, but yeah, you'll feel like you're accelerating up. That's because you're in a centripetal force phenomenon. All right. So that also means there is a larger normal force than your weight because you are being accelerated up on that at that instant. All right, at that instant. Okay, so unit 4, 15 is so conversion of change in potential energy is always the change in kinetic energy. For instance, if you want to calculate how much energy is converted from this specific segment while you're going down like a roller coaster ramp, you want to calculate only this small segment. All right, the change in potential energy of this segment is basically the change in kinetic energy, and then you can get the velocity. All right. Okay. So number 16. If you only consider one ball system, potential gravitational energy is okay. Yeah. Beware of the system calling these like kind of like names in English. All right. So if there is only one ball in the system, potential gravitational energy is ignored. Likewise, like other things, like if you don't consider something that sort, you got to think of the source of energy. You want to ignore those. All right. Number 17, vertical work considers the Earth object system is the same. Oh yeah, yeah. So MGH basically, no matter how much horizontal distance you travel, the vertical work stays the same because there is only one height. All right. So for instance, if the height is this and I traveled this much distance, the difference between there is no difference between this traveling this much distance to get to this height and this much distance. All right. So MGH vertical work is always the same. It is unrelated to horizontal work. Um, okay, number 5. Mm, anything that involves FVT and M should be considered using the impulse formula. Yes. Momentum and so impulse is the difference in momentum is delta P. Yeah. And impulse formula is F times delta T. All right. So whenever you see like any questions with these, you're given a force, you're given a velocity, you're given a time, or you want to calculate like how much time is spent on applying this force. You just use this formula. All right. You got to be reminded of this. This was a like one of the interesting things. I mean, I am really good at momentum personally, so I don't really have to worry about this. But yeah, if you see these words, just know you want to use this formula, like these kind of formula. So but adding something back to unit 4, I thought of something like that's like interesting. When you're walking up the stairs, you're not actually doing any horizontal work. You're just doing vertical work. So yeah, because every time when you step on a surface, you're not actually doing work horizontally because you're just trying to use that stage to get up, right? You're trying to get up. You're not like doing friction to that surface, right? It would be weird to do friction to, but yeah, you're just trying to step up. In an ideal situation, you're never doing horizontal work in the process of walking upstairs. All right, okay. Unit 6, 19. At some instant, if energy is dissipated by another thing, net torque equals. Okay, so for instance, if you have a spinning thing, if you have a spinning thing spinning on over here, and there's friction on the surface, basically the energy will be dissipated. And I like to think there's at some point net torque equals 0 because this surface gotta like have a force to counteract the torque that you have applied to the disc so that at this instant it's gonna stop because of the friction. All right. So basically set up the function as t source minus t object acting on it equals 0, and then start from there. And this is very interesting because net force is sometimes net force equals 0. That is when some force opposes another force and then they become 0 at some point. And yeah, guess what? Torque is just force but in rotational form. Interesting, right? And torque, what is that called? Tau. Tau equals R times F, bro. R times F. And think of what else is R times something. A acceleration is r times rotational inertia, I think. Yeah. Oh, wait. R times alpha. Acceleration is r times alpha, and then velocity is r times angular velocity. That's something interesting. You can think about it. I will not cover that right here. All right. Okay. So unit 7, 20. T and Ts formula is displaceable. So yeah, the period, and you can basically sometimes replace T with Ts or TP formula that is on the formula sheet. Just know that, Ts formula is not like a function, it's just a formula, all right? It seems like a function though. Okay, and yeah. Also sometimes when you wanna like change around t equals 1 over f, because frequency is also like inversely related with period, and the other way around, vice versa. T equals 1 over f equals 1 over t. You want to switch around the k and m, all right? Don't forget to switch around the k and m inside of that root square over there. When you see it, let me just show you. Okay. So yeah, look, this thing. Oh my gosh, dude. Okay, I hope there's no copyright issues, bro. Hold on, bro. Right here. Okay. So look over here. You want to switch around the M and K. I messed up a lot of times. Just not switching this around. Okay. So, okay, 21. Sine spring period position graph occurs on. Okay, so if you have a graph, spring position graph. So if you have a graph like this, you know that when it is at here, it's basically at the equilibrium, all right? So likewise, if you were to have this kind of thing, you start at the equilibrium, but when you use the cosine, so we have two of these, all right? So this is when you start at the, like, let's say positive a, all right? Yeah, this is when you start at the positive a. This, however, is when if you start at here, if you guys start at the equilibrium position, all right? Remember that. That's really helpful. And okay, unit 8 is just fluids. I thought it was really easy. Like, I don't think for this year there's a lot of testings on fluids. Basically, you'll just have to plug in the equations. I will say understand what this is. If you don't understand, just go search it up real quick. I won't explain it here. All right, this is very simple. Just know how to use this. And oh, remember, flow rate is always constant, bro. Okay, so 23. Flow rate is always constant when passing a segment of the tube. Alright, the speed changes but volume stays the same, alright? So look at this graph. Q equals V over T. This is just, this is the formula, alright? Q equals volume over T. And volume equals A times this distance, this height over here, I guess. And what is distance over T? It's V. So that's how you get this formula right here, all right? So A1V1 equals A2V2. And yeah, this is why flow rate always stays the same. So understand that formula. And yeah, you're good. And that's pretty much the video of my day 3 progress. And I'll see you later in my second video today.